Hello chemistry students, this is Dr. Tellis. We are finishing up this chapter with the last two sections. This is about appreciating the connection between the structure of a compound and its acidity or basicity. One of the most interesting aspects of chemistry is the correlation between a molecule's structure and bonding and its chemical properties. Because acids and bases play such a key role in chemistry, principles relating acid or base character to structure will be useful. Let's look at halide acid strengths. HF versus HCl, HBr, and HI. Experiments show that the acid strength increases in the order of HF being much weaker than HCl, hydrobromic acid being even stronger, and hydroiodic acid being the strongest. The stronger acids result when that H and then the halide bond is readily broken. And when it's readily broken, we see that by a smaller, more positive value of delta H. If it's more readily broken, it takes less energy to break that bond. And we can see the acid strength increases going in this direction. And we have a more negative value for the pKa. More negative as I go to the right as strength increases. Acid strength is dependent on how easily the H plus ion is lost or removed from an acid in that formula. As you go down the group in the periodic table, the size increases. For example, if I looked at the periodic table, we know fluorine is on the top right, and then chlorine, and then bromine, and then iodine. And as I go down a group, my size gets bigger and the bond strength decreases. That means our acidity strength is increasing, because if that strength is decreasing, it's going to be easier to break that and remove that hydrogen ion. We know fluorine is the most electronegative. So if electronegativity is increasing, then we're going in the opposite direction. Bond polarity increases and the acid strength will decrease, because we know acid strength is increasing as we go down. For oxyacids, and I'll show you that here in a second, acid strength increases with the number of oxygen atoms. In polyprotic acids, acid strength decreases with more negative anionic charge. Let's look at oxoacids. Acids that contain oxygen, contain at least one other element, have at least one hydrogen atom bound to the oxygen, and form an ion by the loss of one or more protons. For example, I have hydrogen and then I have NO2. I have hydrogen and then I have NO3. Acid strength increases as the number of oxygen atoms increases. So I have NO2, NO3. My HNO3 is going to be stronger. Acid strength increases compared to HNO2 and HNO3. Here's another example where I have one oxygen. These two both have two oxygens, and this has three oxygens. And the difference here, we would need to look at formal charge and resonance that would play a part in those strengths. Why are carboxylic acids Bronsted acids? Well, there's a large class of organic acids, like acetic acid, that have that carboxylic acid group, the CO2H, and that's a carboxylic acid. The arguments used to explain the acidity of oxoacids can also be applied to carboxylic acids. The OH bond in those compounds is polar, which is a prereq for ionization. So if I look at this carboxylic acid here, we know hydrocarbon bonds are not going to be broken in water because those are nonpolar, but polar OH bonds is going to be broken when water is involved. So that is able to be strongly attracted to my water, breaking off to form that H3O+. And then I can have two different options due to resonance. I can have my double bond on this oxygen, or I can have my double bond on this oxygen. The acidity of carboxylic acids is enhanced if electronegative substituents replace that hydrogen. Like if I have a chlorine that replaces that hydrogen. And then let's look at those acids where hydrogen is replaced with a more electronegative element, like that chlorine. Notice that my acid strength increases if I have one chlorine versus two chlorines versus three chlorines compared to just acetic acid with no chlorines. The acetic acid with no chlorine is the weakest. Add more chlorines or more of the substituents, and acid strength increases. The last section is looking at characterizing a compound as a Lewis base, which is an electron pair donor, or a Lewis acid, which is an electron pair acceptor. A Lewis acid can accept a pair of electrons from another atom to form a new bond, and a Lewis base can donate a pair of electrons to another atom to form a new bond. Let's look at the formation of a hydronium ion. If I have H+, well, hydrogen we know has one electron. So if it gives it away, it therefore has no electrons. So H+ has no electrons around it. Let's look at water. H2O has two lone pairs of electrons. So one of these lone pairs of electrons is donating it to that hydrogen. Therefore, the H+ is the electron pair acceptor, giving it the name acid, the Lewis acid. And the water is donating the electrons, so it is the Lewis base. And then I have H3O+. All Bronsted-Lowry acid-base reactions can be characterized as Lewis acid-base reactions. Metal cations, like Fe+2, interact with water molecules to form hydrated cations, like this. Fe+2 forms 6 coordinate covalent bonds to water, and the combination of a metal ion, which would be a Lewis acid, with Lewis bases like water and ammonia lead to what's called a coordination complex. Metal cations, like we just said, often act as Lewis acids because they have open d orbitals. Here's an example where it's cobalt +2, but because of the +2, it gave away 2 electrons that were in the d orbital. So now it has open d orbitals to form that complex. Here's pictures of all sorts of different examples with iron and cobalt and nickel and copper, beryllium. You can see how they all combine and form those coordination complexes with water. The Lewis acid-base concept also accounts for the fact that oxides of nonmetals like carbon dioxide and sulfur dioxide behave as an acid. Here's CO2. We know that CO2, oxygen is more electronegative than carbon. So both of the O ends of this compound are slightly negative, leaving that carbon slightly positive. That means that if it's by a Lewis base like hydroxide, OH-, that OH- with the carbon that's slightly positive allows that OH to attack, and then that OH is able to bond to that carbon. So there's my original CO2, but the OH wants to attack and join right there. So that double bond then forms 2 single bonds. We know ammonia behaves as a base, but ammonia is the parent compound of an enormous number of compounds. They behave as Lewis and Bronsted bases. And these molecules all have that very electronegative nitrogen atom that has a partial negative charge that's surrounded by 3 bonds, 3 hydrogens, and a lone pair of electrons. But it's that lone pair of electrons that allows the molecules to function as that Lewis base in forming a coordinate covalent bond with an electron-deficient atom, like NH3 does with BF3. BF3, notice right here, there's no lone pairs. So that NH3 with the lone pair is going to form a bond right there between the nitrogen and the boron. We can also look at, here's our NH3, and here I have H2O. The nitrogen is partially negative. It can just extract that proton from water because there's strong hydrogen bonding between that electronegative nitrogen and the slightly positive end of hydrogen. And that wraps up chapter 16.